In this video, I will describe in some detail how the Atari 5200 automatic RF switch works. Let's start off by understanding what the automatic RF switch is used for. To put it simply, the automatic RF switch is used to select an input source for the TV's antenna input connection. The input source would normally be an antenna or cable box for watching TV, or the Atari 5200 for playing video games. Back in those days, there were still a lot of people using TV antennas over cable. Shown in this table are the possible antenna input sources for the TV when connected to an Atari 5200 automatic RF switch. When the 5200 is powered off, the TV antenna or cable box would be connected to your TV's antenna input, while the 5200 would be disconnected from your TV's antenna input. Likewise, when the 5200 is powered on, the TV antenna or cable box would be disconnected from your TV's antenna input, while the 5200 would simultaneously be connected to your TV's antenna input. How this all works will be explained using the following schematics. Shown in the top left corner of the schematic is the external power supply for the 5200. On the bottom of the schematic are the power switch logic, linear power regulators, and RF modulator that are contained within the 5200. On the top of the schematic is the external RF switch box. Physical switching of the TV antenna or cable box and the 5200 console is performed by a relay. The relay contacts are shown here boxed in red. When the relay is unenergized, the contacts on the left are normally open, thus disconnecting the 5200 from the TV's antenna input. These contacts will close once the relay is energized, thus connecting the 5200 to the TV's antenna input. Likewise, when the relay is unenergized, the contacts on the right are normally closed, thus connecting the TV antenna or cable box to the TV's antenna input. These contacts will open once the relay is energized, disconnecting the antenna or cable box from the TV's antenna input. The relay coil that controls these contacts is signified by the circled letter K. The relay is controlled by an LM393 comparator. The non-inverting input, signified as IN+, is tied to a reference voltage generated by this voltage divider. When the voltage on the inverting input is greater than the non-inverting input, the output of the comparator is driven low. When the output of the comparator is driven low, it forward biases the 2N3906 PNP transistor, driving it into saturation, pulling one side of the relay coil K to approximately ground level. This in turn energizes the relay. When the voltage on the inverting input is less than the voltage on the non-inverting input, the output of the comparator will float, causing the 2N3906 transistor to turn off, thus disconnecting one side of the relay coil. This in turn de-energizes the relay. How the inverting input of the comparator gets its signal input is not immediately apparent. By taking a closer look at the schematic, you can see 2.33 ohm resistors connected in parallel. One side of these resistors is tied to the external power supply ground, while the other side of these resistors is tied to the female RCA connector outer conductor. When the male RCA connector from the 5200 is mated with the female RCA connector on the RF switch box, the ground on the 5200 is separated from the external power supply ground by 2.033 ohm parallel resistors. What this does is place these resistors in series with the ground pins of the LM340T linear regulators. As return current flows through the ground pins of these linear regulators, the current is also flowing through the 2.033 ohm parallel resistors. When current flows through these resistors, a voltage drop is developed across them. The voltage is then fed back to the inverting input of the comparator through a 100k ohm resistor. In the next video, we are going to look at the hardware fix that I did to get the RF switch working again.